And welcome to our study of simple harmonic motion. Today, we're just going to look at the very first parts of simple harmonic motion and look at some information on Hooke's law, period and frequency, and the energy involved in simple harmonic motion when it comes to springs. So, when I'm talking about simple harmonic motion, what is that? Well, think about it this way. If you attach a weight on a spring, okay, a spring that is a vertical spring, and you attach a weight, and you release that weight, what are you going to do? Or what are you going to see? You're going to see that weight bounce back up and down and up and down. The weight's going to bob up and down with a reproducible period. Your period is your measurement of t. And you can plot your position versus time graph. And when you do that, the graph is going to resemble a sine or a cosine function. So when you're looking at your equilibrium position, if you release it from your maximum position, say you pulled it down, then what's going to end up happening is you have a sinusoidal or a cosine type graph. And actually, this is going to be way more consistent. So you have a maximum displacement here is equal to your maximum displacement there, and so on and so forth. Okay. And that's going to be considered your amplitude of your simple harmonic motion. So your simple harmonic motion is the cyclical motion. Springs and pendulums are perfect examples of simple harmonic motion. So when you're looking at periodic motion, what is periodic motion? That's when a body moves back and forth with a fixed path over a definite interval. Okay, so if we're looking at planetary motion, your planets are following a fixed path that's repeating itself. Now, harmonic motion is periodic motion, but there's no friction. So with no friction, you have this restoring force that's pulling it right back to its original displacement. So everything's going to be the same displacement. So again, you're going to have something like this, where your amplitude is going to be the same on the top and bottom. Okay, so your equilibrium position is this position right here. It's the length where no force is exerted on the mass. So at that point, I have been restored to my equilibrium point. Now, damped harmonic motion, what is that? Well, when I have simple harmonic motion, you have your constant, okay? And so all of this I am drawing over and over again, trying to show you that simple harmonic motion, you're going to have the same amplitude on the top and on the bottom and through the entire thing. There's no friction. Well, damped harmonic motion is when there is some kind of friction or like air resistance. So damped harmonic motion is going to look like this. Okay, where your wave is going to end up kind of fizzling out. That's going to be damped harmonic motion. And it's because you have air resistance or some kind of friction that's causing that wave to not meet the same amplitude each time. Okay, so when we're looking at a graph of our wave motion, when we look at this, we're looking at first our equilibrium position. Our equilibrium position, again, is that point where you have no force, no restoring force acting on it. Okay, so if there's no restoring force, well, we know something we know about force is force equals mass times acceleration. So if there's no restoring force, then your acceleration is going to end up being equal to 0 at that point. Okay. Equilibrium is where kinetic energy is maximum and potential energy is 0. Okay. Well, think about it this way. At the top here, we have our potential energy is going to be our 1/2 kx squared. Well, if our x is maximum here, then you're going to have maximum potential energy. Right here, your x equals 0. If your x equals 0, then your potential energy of your spring equals 0. Okay. And then if your potential energy is equal to 0, then your kinetic energy must be maximum. So go ahead and draw this wave. This wave is showing you what are the components of our wave. So here we have the wavelength. The wavelength can be any points that are repeating. So my wavelength could be something like starting right here and then going to here. Notice I'm showing crest to crest. So you can do crest to crest, trough to trough. The trough is this bottom part right here. So wavelength is going to be the measurement or the length until the wave starts to repeat itself. And so wavelength, the symbol for wavelength is that upside down Y looking thing. It's called a lambda. Your amplitude is going to be your displacement or your maximum height. And then your undisturbed state is going to be your equilibrium. Your crest is your highest point. Your trough is your lowest point. So when we're looking at springs, we are going to be looking, in this course, we're going to be looking at specifically ideal springs. So ideal springs are considered to be massless, meaning we're not going to take mass into consideration when we're looking at ideal springs. Ideal springs are both compressible and extensible. So you can compress them and you can extend them, and they follow Hooke's law. So when stretched or compressed away from equilibrium, you're going to have a restoring force. So if I have my spring here, say that's where my equilibrium is, and I grab on that spring and I pull that box down, what I have done is I've pulled it away from its comfort spot, from where it's comfortable. So this right here is going to be my displacement, how much I've displaced it. Well, when I've displaced it, what's the spring going to do? As a reaction, the spring is going to want to pull up on that. So that's going to be called your force of your spring or your restoring force. So when we're looking at Hooke's law, and we did look at this previously in previous lessons, but Hooke's law, notice, is negative kx. The reason it's negative is because it's showing you it's in that direction. It's in the direction opposite of your mass times gravity, or opposite of your pull. So it's not necessarily the negative that's important. It's just understanding what's the direction of that. Okay, so when you're looking at Hooke's law, remember Hooke's law is negative kx or just kx. Force depends on your position, so it's not going to be constant. And so acceleration is not constant throughout the entire restoring process, right? Because your force is going to be changing throughout the spring, because your X is changing. Now your K is your spring stiffness. So for example, if you have like a dart gun or a Nerf gun or something, you have a spring that's causing the darts to kind of fly through the air. Now think about that kind of spring if you've ever taken a dart gun apart versus the springs on your car. Which one is going to need to be more stiff? Your car is obviously going to need to be more stiff. The looser that is, the looser your suspension is, or the lower your K is, the more your car is going to bounce up and down and up and down when you go over speed bumps. So the larger the K, the more force needed to move it. Okay. So a car is going to have a large K. A dart gun is going to have a low K. So let's look at this sample problem just real quick. Just a quick multiple choice question. You wish to double the force constant of a spring. What do you think you can do? Double its length by connecting it to another one just like it, cut it in half, add twice as much, and take half of the mass off. Which one do you think is going to happen? Well, what's actually going to happen is if I cut it in half, then that is what is going to change my force constant. It's going to double my force constant. So only by cutting it in half, that's how your force constant will change. So let's look at our in-class practice problems. Our in-class practice problem number 1 says a certain spring has a relaxed length of 5 centimeters. So that's going to be its equilibrium position, but stretches to a new length of 7 centimeters when a 90-gram object is hung from it. What is the spring constant of this spring? Well, we want to figure out what is our K value. we know force is equal to kx. Notice I didn't use my negative because really I'm just looking at what is the restoring force. And I know that's going to work in the opposite direction. So what is my force being applied? Because here I have my box, we'll say, pulling. And so I have mass times gravity pulling down. And then I have my force of my spring pulling back up. So my force is equivalent to my mass times gravity, and that's equal to kx. So my k is equal to mass times gravity divided by x, where x is my displacement, how much I've displaced it. So my mass is going to be 90 grams or 0.09 kilograms, because remember, we always want to be in kilograms in physics. And then my gravity is 9.8 meters per second squared. And then finally, my x is going to be my change in position, which is 0.02 meters. When I go ahead and plug all of that in, I end up getting my k value is 44.1 newtons per meter. Okay. So my next question says, now the 90-gram object is removed. So I've removed this 90-gram object, and a different object is hung from the same spring. If the spring's new length is going to be 11 centimeters, okay, what must the mass of the second object be? So I'm going to use my F equals kx, but my F has changed. I have mass times gravity equals kx, and I'm trying to solve for my new mass. So I take my kx divided by gravity, and my k, remember, is a constant. So my k has not changed. It is 44.1 newtons per meter. Now, what is my x? My x has changed. I've gone from 5 centimeters to 11 centimeters. So my x is going to be 0.06 meters. And then my gravity is 9.8 meters per second squared. So my mass ends up being 270 grams. I have replaced it with a 270 gram mass. Now, is there a different way to solve that? Yeah, you can look at it in terms of proportions, and in terms of like, how is F related to my x? Okay. And so I know that my x, instead of being 0.02, I've now made that 0.06. So I've multiplied it by 3. If I've multiplied my x by 3, then that means that I've multiplied my force by 3. Okay. And so I took my force, my 90 grams, I multiplied that by 3, and I get 270 grams. So when I'm displacing a spring, I could displace a horizontal spring. So what are my positions that are really important? Well, my amplitude is related to my maximum displacement. Okay, so amplitude is going to be my maximum displacement, and that displacement is the distance from my equilibrium. So if this is my equilibrium, then this is my maximum displacement. And what that's going to end up telling you is what my energy is, because my energy, my maximum energy, is going to be equal to my potential energy in this situation, because I don't have gravitational potential energy. And so it's going to be my spring potential, which is 1/2 kx squared, okay, which in this case is equal to 1/2 Ka squared. So my maximum energy is going to be, or my total energy of my system is going to be equal to 1/2 Ka squared. So what about velocity? Well, when I'm looking at the velocity, I have my equilibrium position and I have my largest displacement. Well, when my displacement is the largest, so my total energy is equal to 1/2 kx squared. That means at that point, my velocity equals 0. So at my maximum displacement, my velocity equals 0. At my minimum displacement, 1/2 kx squared equals 0 here. And so therefore, my total energy is going to be equal to my kinetic energy in this case, plus my gravitational potential energy. So, but if I look at that, disregarding the gravitational potential energy in the whole problem, we're looking at 1/2 mv squared here. So my velocity is going to end up being max at my equilibrium position. And then finally looking at acceleration. Well, where do I get acceleration? If I look at Hooke's law, and I look at Hooke's law with relation to my maximum displacement or my amplitude, F max is equal to negative Ka. So F max also is equal to Ma max, A being your acceleration max. So if I go ahead and plug and chug here, I know that acceleration is equal to F max divided by M. Well, I've also said that F max equals negative Ka. So I've gone ahead and I've used substitution here to bring me this equation right here. So my acceleration is maximum, my acceleration maximum is equal to negative K divided by M being my mass times X, my maximum displacement. Okay, so going back to your graph of your wave motion, your maximum minimum positions are your peaks and your valleys, or your crest and your trough. Okay, and at that point, you have your maximum potential energy. So now going to this, when I'm looking at my repeating pattern, okay, how do I measure that repeating pattern? Well, I can measure in terms of period and frequency. So period is the length of time required for one full cycle. The length of time required for one full cycle, and we measure that in seconds. Now, something that we looked at in the last video is remembering that velocity equals distance divided by time. So if you're looking at your sinusoidal motion, your distance kind of can follow a circle. And so what's the distance in a circle? The distance on a circle is 2 pi r, or the circumference. So 2 pi r divided by period, or time, is equal to the velocity. Okay, so if I bring period over here, 2 pi r divided by velocity. Okay, well, when I'm looking at circular motion or angular motion, I know that omega is equal to v divided by r. Okay, so right here I have r divided by v. So if I find the reciprocal of that, I end up getting, through substitution, the period is equal to 2 pi divided by omega. And that's going to come in handy as we move on through these lessons. So frequency, what is frequency? Frequency is how fast an oscillator is oscillating. So if I look at wave motion, okay, if I'm looking at a wave like this, okay, or I'm looking at a wave like this, this one has a much higher frequency, right? There are more cycles or more waves that pass per second than in this one, okay? So frequency is equal to 1 divided by the period, and the measurement is in hertz, okay? So 1 hertz is equal to 1 divided by seconds, okay? And that's what this seconds to the -1 means. So what factors are going to affect the period of a spring? Okay, well, let's think about that. If we think about the period, the movement of a spring, okay, what do you think is going to affect that, and what is not going to affect that? Okay, well, when we're looking at these different factors, we could look at the mass. Okay, mass is going to end up affecting it. Your spring constant is going to end up affecting it. Okay, what is not going to affect your spring, your period of your spring? Amplitude will not affect the period of your spring. Okay, so when we're looking at the period of the spring, the equation of a spring is T equals 2 pi times the square root of m over k, where T is your period, m is your mass in kilograms, and k is your force constant. So what about gravity? Does gravity affect the period of a spring? No. G is not included. So note no G, and no amplitude. Okay. So let's look at the sample problem. It says an 80-gram mass is attached to a spring hung vertically, causing it to stretch 30 centimeters from its unstretched position. If the mass is set into oscillation on the period of the spring or on the end of the spring, what will be the period? Well, we know that period is equal to 2 pi square root m over k. Well, I'm given my mass, but I'm not given my k. So I need to solve for my k. My k is solved for by using Hooke's law. So we know that the restoring force is equal to kx. And that restoring force is also equal to your mass times gravity. Mass times gravity equals kx. So to find our k value, I do mass times gravity divided by x. Okay, so in this case, I'm going to end up pulling my 2 pi square root of my x, which is 30 centimeters or 0.3, divided by 9.8. Okay, so looking at your in-class practice problems number 2A, it says a certain spring stretches 5.2 centimeters when a 200 Newton weight is hung from it. The weight is then displaced from equilibrium and set into oscillation. What are the period and frequency of vibration of the mass spring system? So let's look at that. Well, I know I'm looking for period. Period equals 2 pi square root of m over k. And I know it has stretched by 5.2 centimeters. A 200 Newton weight is hung from it. The weight is then displaced from equilibrium and set into oscillation. So let's see what I can do. Do I know what my mass is? Well, my mass is 200 divided by 9.8. Okay. Do I know what my K value is? Well, I'm not really sure what that is. So I need to look at the information that I'm given. Okay. So I know that force is equal to Kx. And so I know my force is 200 newtons. 200 newtons is equal to K times 0.052 meters. That's going to end up giving me a K value of 3,846 newtons per meter. And I'm going to use that information and I'm going to plug it in here. So I end up getting that the period is 2 pi times the square root of 200 divided by 9.8, because remember your force equals mass times gravity, divided by 3,846 newtons per meter. That's going to end up giving you a period in this case of 0.458 seconds. Now, I'm not finished with this question because it says, what's the period and what's the frequency? So what is frequency? Well, frequency is equal to 1 divided by period, because period is the amount of time per cycle, whereas frequency is cycles per time. Frequency is cycles per time. How many cycles will go through per unit time in like a second or in a minute? So how frequently do the waves pass? What value of K would a spring need in order for 100 Newton weight to vibrate with the same period? Well, let's think about that. I'm looking for what's my K value. So I know period equals 2 pi times the square root of m over K. Something I like to do is manipulate my equations first. So I'm going to go ahead and manipulate my equation first. I get T over 2 pi is equal to m over K. And then I'm going to square both sides. Okay. Don't lose values here. So I have T squared equals 4 pi squared, and that or divided by 4 pi squared equals m divided by K. So I'm going to switch the position of my K and my T because I'm looking for what value of K. So I end up having K is equal to 4 pi squared m divided by T squared. Okay, so my K value is equal to 4 pi squared times M. My mass is 100 divided by 9.8 divided by T squared, and my T is 0.458. Square that, I'm going to end up getting a value of 1,920 newtons per meter. Okay. Now, there are a couple of things that are important for you to remember about springs. First off, period is proportional to the square root of m, because remember, T equals 2 pi square root of m over k. So as m goes up, your period is going to go up. Period is proportional to 1 over k. So as your k value goes up, your period is going to go down. And why is that? Well, because the spring is harder to compress or to extend. And because of that, your period of motion is going to be smaller. Okay. Period does not depend on amplitude. It is so important for you to know that. Period does not depend on the amplitude. Okay. So when I'm looking at springs or pendulums, I'm also looking at conservation of energy. And we actually spent quite a bit of time talking about springs when we talked about conservation of energy. We also talked about pendulums. Okay. The equilibrium position has kinetic energy, high kinetic energy, and low potential energy. Okay. Because when you're looking at your total energy in a system, you can look at 1/2 mv squared. You can look at mgh, which is your gravitational potential energy, and you can look at 1/2 kx squared. And your x is going to be your displacement from your constant. Now, this is something that we looked at for our total mechanical energy when we did conservation of energy. Okay. Now, the total energy of your oscillating system is going to be constant. So if you have a maximum x, that means that these right here are going to be crossed out. If you have a maximum v, that means your x must equal to 0. So when I'm looking at the positions of energy on a spring, okay, here I'm looking at, say I have my displacement. So I'm at equilibrium, I'm at my maximum displacement. At my maximum displacement, I have my maximum potential energy and my minimum kinetic energy, okay? At my minimum or my equilibrium position, I am going to have 0 potential energy. Why? Because potential energy is related to 1/2 kx squared, okay? And your kinetic energy is 1/2 mv squared. So your kinetic energy is going to be maximum when your potential energy is its lowest, its 0 value, okay? And then here, where my potential energy is high, kinetic energy is low, it's at 0, okay? So this graph is very important for you to understand. It's very important for you to be able to graph your position, graph your potential energy, and graph your kinetic energy of a simple harmonic motion system. Okay, so when I'm looking at that energy during simple harmonic motion, we just talked about that. When you're looking at a horizontal spring, so I have a spring that's like this, okay? Well, there I don't have gravitational potential energy. So I have my kinetic energy initial, which is 1/2 mv squared, plus my 1/2 kx squared. Okay, and then that's equal to my kinetic energy final and my spring potential energy final. When I have a vertical spring, so something like this or something like this, I take into consideration gravity. So remember, gravity is mgh, okay? But this is how you break down your mechanical energy of a spring system. So looking at that, when I derive this equation, 1/2 mv squared plus 1/2 kx squared is equal to 1/2 ka, a being your amplitude, okay? A being your amplitude. Your amplitude is your maximum x. When you manipulate that whole equation, you find that your frequency does not depend on amplitude. Okay, so let's look at this sample problem. A spring of force constant K equals 200 newtons per meter, and it's attached to a 700 gram mass oscillating between x equals 1.2 and 2.4. Where is the mass moving the fastest? Okay, and how fast is it moving at that location? Well, I want to know where it's moving the fastest. So my potential energy is equal to my kinetic energy at that fastest point. Okay, that fastest point is going to be 1.8. It's going to be that, if you look at this is going to be 1.2 meters. That halfway point is your position of equilibrium. Okay, so you have 1/2 kx squared equals 1/2 mv squared. So to figure that out, then you go ahead and plug and chug. I cancel out my 1/2s, so I end up getting kx squared equals mv squared. Your velocity max is going to be kx squared divided by m, and you take the square root of that. That's going to give you 10.1 meters per second. Okay. A spring of force constant K equals 200 newtons per meter is attached to a 700 gram oscillating mass going between 1.2 and 2.4. What's the speed when you're at the 1.5 meter point? Well, 1.5, you need to figure out what's your displacement from your equilibrium. Your displacement is 0.3 meters. Okay, and so you are trying to figure out what is the speed at at that point. Well, you find your maximum. Your maximum is 1/2 kx squared, and then that's equal to 1/2 kx squared at that position plus 1/2 mv squared. When you manipulate everything and plug and chug, you're going to end up getting 8.78 meters per second. So let's look at an example problem for ourselves. A 5 kilogram mass is attached to a horizontally oriented spring. The constant is 1800 newtons per meter, and it undergoes simple harmonic motion with an amplitude of 80 centimeters. Okay, what is the total energy of the system? Well, the total energy of the system is going to be your maximum potential energy. Your maximum spring potential energy is going to be your total energy. So that's going to be 1/2 Ka squared. Well, your amplitude is 80 centimeters. So that's going to be 1/2 K, 1800 newtons per meter times 0.80 squared meters squared. That's going to end up giving me a maximum of 576 joules. Okay. What is the speed of the mass when it passes through equilibrium? So when it passes through equilibrium, what is that speed? Well, I know that my total mechanical energy, okay, so my mechanical energy initial, we'll say max, is equal to 1/2 mv squared plus 1/2 kx squared. Well, at equilibrium, x squared equals 0. Okay, so I know that my 576 joules is equal to 1/2 times my mass. My mass in this case is 5 kilograms, v squared. And my v ends up to be 15.2 meters per second. And then finally, how fast is the mass moving when the spring is compressed 30 centimeters from equilibrium? So again, I have my mechanical energy initial is equal to 1/2 mv squared plus 1/2 kx squared. So 576 joules equals 1/2 5v squared plus 1/2. My K in this case is going to be 1800 newtons per meter. My X is going to be 0.3 meters squared. Okay. And when I manipulate that, so I get 900 times 0.3 squared. And then I'm going to bring that to this side right here. And I end up getting that my velocity is equal to 14.1 meters per second. Okay. And then our very last in-class practice problem for today is looking at labeling different positions on this graph. So here I have my maximum displacement, or my amplitude, my minimum in this case, my maximum here. It says a mass spring system is constructed by connecting a 0.2 kilogram object to a horizontally oriented spring with a force constant of 450 newtons per meter. The mass is displaced from equilibrium and released to oscillate in simple harmonic motion. The diagram below is a graph of the positions reached by the mass during the cyclical motion. Label the locations on the graph where the mass experiences its maximum position. So this right here is going to be your maximum position. This one is going to be your maximum position. Okay. Speed. Okay, and acceleration. So when we're looking at speed, at our maximum position, velocity equals 0. Okay, and then acceleration. Well, when I'm looking at acceleration, my acceleration is going to be the greatest at my maximum displacement, and that's because force equals mass times acceleration, and force in this case equals kx. So when we're at our maximum displacement, we're at our maximum acceleration. So acceleration is max here. Acceleration is max here. And acceleration is 0 at your equilibrium position. Okay. And then if your velocity is the smallest here, with your x is your minimum here. And so therefore velocity is your maximum here. Your velocity is your maximum at your equilibrium position. So it says if the mass is moving at 5.5 meters per second at a location of 7.2 centimeters, calculate the values of maximum position. So x max, velocity max, and your acceleration max. Okay, so x max, what are we going to end up doing for that? For that one, we're going to look at 1/2 mv squared plus 1/2 kx squared equals 1/2 ka, which is going to be your maximum position. I'm going to cancel out my 1/2s, okay? And I'm going to end up getting mv squared divided by k plus kx squared divided by k. So my k's are going to cancel. And this is a squared. So we're going to take the square root of that is equal to a. So I'm going to end up taking m, which is going to be my mass of my object, which is 0.2. Velocity is 5.5 squared divided by my 450 plus my x, which is 0.072 meters squared. And that's going to end up giving me my maximum displacement is 13.6 centimeters. Okay. Now my Vmax is where my mechanical energy initial equals my mechanical energy final. My Vmax, 1/2 mv squared is equal to 1/2 ka squared. Okay, so when I'm looking at that, I know that my maximum energy is going to be 4.19 joules equals 1/2. My mass, again, my mass is going to end up being 0.2 v squared. So my velocity max is equal to 6.5 meters per second. And then finally, my acceleration. Well, how do I figure out my acceleration? Well, remember, I have F equals ma. Okay, so at your maximum force, you have your maximum acceleration. And we also know force equals kx. And you have your maximum force at your maximum position. So you end up having ma max, okay, is equal to your kx, okay? So then you end up having acceleration equals kx divided by m, okay? And your k, remember, is 450. Your x is going to be your maximum position, which is 0.136, divided by your mass. Your mass is 0.2, and that's going to end up giving you your maximum acceleration is 306 meters per second squared. Okay, hopefully that was very helpful for you. If you have any questions, please make sure that you reach out. You know where to find me. Thank you.